in the chat if you can hear me. Hello. All right, so I guess you can hear me. Let's give it a minute or two. Maybe a few more people are gonna show up. All right. So the plan for today includes the following. Just going a little bit over the Linux file system, basically reviewing the inode structure. Then looking at Windows file systems such as FAT and NTFS, see how they are structured internally. Talk a little bit about a few more file systems. And then just a very brief look at how you would implement exchanges with the hard drive, not SSD, but hard drive. And then clarify, maybe retell the story of the Pathfinder in a way that might be a little more accessible to you. And then discussions about exams and such, and then that's it. All right, so let's get started. So last time we talked about the Linux file system, and we've seen that files have a so-called inode, which is basically an entry point from where you can find the blocks of data that the file has. And you have this structure where small files would fit into this directly linked blocks. Larger files would have to go through one indirection. Basically, the link from here doesn't go to data, but goes to a block of addresses which point to data. If the file grows beyond this, then you have a double indirection, a block of addresses pointing to other blocks of addresses, which in turn point to data. And finally, if it really gets that big, that large the file, then you have the triple indirection. So this is in Linux the entry point to a file. And there is this identification stuff right at the beginning of the inode, which contains things like ownership, who owns the file as a user and as a group, what are the permissions, and a few other things. All right, file size, access times, modification times, and so on. And then files are grouped in directories as such. Basically, directories are files containing a list of file names and inode numbers. All right, so that's it. Now, if we are to look at Windows, Windows has a different kind of file system organization. It has an older one, which is called FAT, and it has been the file system of MS-DOS, which, being a single user, single tasking operating system, did not need any kind of security at all. The notion of ownership did not exist. The files did have some attributes, things like read-only, but nothing like permissions that you have in Linux. So this FAT file system is really popular even today with this portable drive that you would need to connect to other computers, basically it's popular because you don't have trouble with permissions. You can go to any operating system and it will match. The problem with it is that it's limited in size. You cannot have very large file sizes, and also is not the most reliable. So let's have a look at how it's organized. If you recall, let's see if I can pull the image. So this is how the Linux disk looks like. You have the boot block, and then a super block describing the geometry of the partition, and then a zone with inode with with inodes, and then a large area with data. So this, you'll see, it's actually somewhat similar. You have here, just like on the other side, a boot sector, and then what we call their super block and inode area, you can regard this as the FAT. Okay, now FAT means file allocation table. So the idea of the FAT file system is really simple. You have a large space where you store data, and then you have a smaller map in which you mark, in which present, thank you. I've been known to talk about trendifiers as well, which also it's not really English. Let's see. So the FAT, the file allocation table, is like it's a map basically of what's occupied in the data area. In a way, you have the data area grouped in something called clusters, which are large chunks of data, and then the FAT is just an area where you have addresses of these clusters and organized in linked lists of how they belong to files. You also have a copy of this file allocation table. This was usually the problem with FAT. If the power went off, you may get a corrupted FAT or an inconsistent FAT, and then you'd lose files because you wouldn't know how to find their data on disk. So then you'd keep a copy that would help you, rebuild the FAT. And then you have the root folder. So practically, this is the entry point. The root folder would contain records of the files that are just in the root, right? And then those files would point to you'll see what those mean, how the files will find their data. There will be subdirectories in the root, which would contain then sublists, other lists of files, and so on. But the root directory is where you would start. Now, what's in the FAT? Not here, here. So as I told you, the file allocation table is basically like a map of the data area. And in a directory, you would have a pointer, right, to the first block of a file, the first cluster of a file. Okay, so a small file will fit in a cluster. If it's larger, you get another cluster and another and another. So practically from the directory, you get the entry point. This file, file1.txt, starts with cluster 2. So you can go to the data area and read cluster 2. But then, if you need the next cluster, you have to come to the FAT at position 2, same as the cluster number, and find there the address of the next cluster, which in this case is 3. So now you go back to the data area and you get cluster 3. If you need the next one, you come back to FAT, you go to 2, you go to 3. Okay, the next one is 4. You go to the disk and you read cluster number 4. And then if the address in the FAT is FFF, actually, if it's between FFF8 and FFFF, that means it's the last That's the last cluster in the file. So if you look at it, it's really a linked list of clusters. A file finds its data using a linked list. Now this linked list is not contiguous. You can see in the case of file 2, it has two clusters next to each other, 5 of 6, but then the next one is 8. And in the middle in cluster 7 is file 3, which means most likely that the last cluster of file 2 was written after file 3 was created. And that's it. Now, accessing FAT files is not very fast because you have to keep working in the FAT and keep iterating through that linked list of clusters. If the file gets corrupted, if the FAT gets corrupted, you kind of lose track of files, and you can get mixed files, right? You can get a block from another file appearing to belong to this file. If the disk gets really fragmented, then a file would mean you have to jump all over the place after it, and that's where defragmentation comes. It kind of brings the whole file together in one contiguous linked list. One, let's say, good thing about FAT was that if you deleted the file, and when I say delete the file, I don't mean pull it to the trash bin. There was no trash bin back then. There is no trash bin in Linux, really. So if you delete a file, if you go to the command line and say delete, just like in Linux you say rm, that file is gone. In Linux there is no way to bring it back. There are some tools that specialize in this, but it's not something that you just easily do. In MS-DOS, you had a command named undelete, which would undelete a file, but that meant it actually analyzed the FAT table and would try to guess where is the beginning of the file that you want to undelete. Because this links list would be left in place, just the head of the list would be deleted, right? This sometimes resulted in bad files because the whole thing would get mixed up if there were other disk writes. But other than that, there was no real benefit except for the lack of security, which makes it popular today. So this is how FAT lives. Much smaller files, not very performant, no security. So this is when I was a kid, I was playing with MS-DOS, so this existed even then, just like the Linux file system. Now, at the point, Windows became mature enough to act as a server operating system, and they needed a new file system. So they came up with NTFS, which comes basically from the notion of Windows NT, Windows New Technology. This disappeared, but disappeared just before 2000. Windows 2000 replaced it. But a lot of it is still present, right? So NTFS is the file system for Windows NT. And this came with a different way of storing data. So you can see the volume structure here. Again, somewhat similar to what you've seen before. The first sector is always the boot sector, so that's expected. But then you have this so-called master file table. Now this is different from FAT and is different from inodes. This is, they call it a relational area. You may think of it like a relational database, but I'm not sure of the details. So this is like a map. The master file table is a map of what files you have and where their data is. And then you would have right next to it the system files, which are privileged in a way so that they work faster, I guess. And then you have the large file area. So let's see what's Berzan saying. Oh, okay. So he has a question about. All right. So let me clarify this. How can you use a byte and a half? You simply use 12 bits. That's it. You work with bit masks. So it's all about the address. how many, so the largest file you can, sorry, the size of the disk, the maximum size of the disk is determined by how large your cluster is and how many clusters can you address. Okay, so here you have a map of the whole data area. Every cluster has an image here. Now, if your address is 1.5 bytes, that means 12 bytes, that means 2 to the 12th minus 1. So that's what? 4098 clusters. That's the largest disk size you can have. That's all there is. Yeah, and then they switched to FAT32 where you can have about 2 billion clusters, right? And the cluster turned out, I'm not sure what the size of it was. Anyway, with FAT32 you can have pretty large fat disks, but with FAT16 I don't think you could go beyond 4 gigabytes. Because the address would be 16 bytes, which is 65,000 clusters, and the cluster would probably be a few kilobytes and you'd get 4 gigabytes. Yeah, so the 1.5 is not the size of the cluster, it's the size of the address. Now here the master file table is working on 32 bytes, maybe even 64, I don't know this detail. And that's the part of NTFS that we want to look into. So this master file table is like an index to the files, but it's a little different. While before, an inode is a rather small structure. The FAT, it's actually a bunch of addresses, not very large either. Here, the master file table is a large thing. It's large enough that it can contain the whole of a small file. So what they try to do is to treat small files in a privileged way. Small files will not have to search for their data. They will not have to go through links to reach their data. The whole small file is straight here in the small file table, in the master file table. If the file is larger and it doesn't fit, then its clusters are referred to using a B tree stored here in the record. Or at least the root of it is stored in the record. A B tree is like a binary tree, but then in each node you have more than one value. So if you have a single value, it's a binary tree, and if you can think of it, if it's larger, you go left. If you're searching for something larger than the value in the node, you go left. You go right. Otherwise, you go left. Now, in a B tree, you can, having multiple values in a node, you have also links in between the values. So a B tree node has more than 2 children. It has n plus 1 children, n being the number of values in the node. So the B trees are extremely performant for finding data. They're also used in databases as indexes. So the clusters of the files are organized in this very performant structure. And small files are straight here in the master file table, so there is no need to search for them. Now, other aspects of the file systems, and NT does those, FAT does not, is how do you write your data to the disk? Basically, if you have to overwrite something in a file, it has a lot to do with what if you lose power? What if the whole system crashes? Will your data be corrupted? Will you lose data? Or will you have data only half written? So then you hear about several kinds of techniques. I'll just mention journaling, in which every operation to the disk is actually written in an area of the disk, like in a log. And only after it's written there, it's made permanent on the disk, which means that if the power goes out, you can replay those things from the file system journal. So if the power goes out in the middle of a write and you have something inconsistent, you can replay this journal and fix things. But even this has its risks, right? There is also a technique called COW, copy on write, instead of overwriting data, a cluster of data, you write your new value in a different cluster. And then once it's written, then you only rewire the new cluster instead of the old cluster. This is used to ensure data consistency. There will be no half writes. Okay, old data is safe. You write the new data and then you rewire. Power goes out anytime. You still have both data and you choose which one you use. You'll find this in ZFS, which is a really advanced file system created by Sun for the operating system Solaris, now belongs to Oracle, and ZFS starts being available, I think even in Mac OS. People try to make it available, but it's all this issue of licensing that doesn't let it become as popular as it could be. So this is about file systems. The last piece, which I will not require for the exam, but I just want to give you an idea, is about how you interact with the disk, with the hard drive. And the hard drive, not a solid state drive, so not an SSD. And it's interesting for you to hear the problems that you have to face, because we talked about, where do you put your stuff in memory, right? And we talked about pages. Where do you allocate memory? And we talked about best fit, first fit, worst fit, and so on. Okay? But this all had to do with RAM, with the technology which allows random access really quick. However, when you work with a hard drive, you're looking at a mechanical contraption that will have limitations simply because it has to move mechanically. So I want to give you an idea of one thing that you may need to do to make it more performant. So let's first look at how a hard drive works. You usually have one disk, but you could have two or three, but let's just work with one because it's the same idea. So you have one disk, and think LP disc. I'm not sure, like a vinyl disc. Maybe some of you had those, right? A vinyl disc is actually has a spiral on it, and it has this fork which has a little, maybe needle, a head, that simply slides on this groove that it has, and it goes spiraling towards the middle. Idea is very similar for hard drive, except that there is no spiral, is just concentric circles, and they're called tracks. Okay, so on this disk you have tracks, just like you have on a CD. You look at the CD, so somehow, hold it against the light, you'll notice these tracks. So in order to read data off a hard drive, what you need to do is to move this head, the needle, if you think vinyl, the head moves like this, slides along the fork. So you have to position the head above the track that you want to read, and then you want to rotate this plate so that the data that you need to read comes under the head. Now this plate doesn't rotate and stop, because that would take even longer. So your hard drive just spins continuously. So practically, in order to read data, you have to have two things that mechanically move, and then the data that you read is actually read in motion. As the track slides under the head reads the data. Oh, you had trouble with I'm sorry, I have no way of influencing that. So it's a continuous process. Now, I remember telling you about this little thing with yelling at hard drives. If you shake your hard drive, you'll affect this mechanical alignment, And you will miss reading some of the data, which means the hard drive will have to wait until the plate spins again and try again to read the data. So if you want to read the cluster, you either read it in one shot, but if anything happens, maybe you shake your laptop, right? And you have a hard drive in it, not an SSD. Then the hard drive has to rotate again. The whole plate has to spin once more and try to read the hard drive again. If you put a large enough magnet, the data is not going to disappear just because you stop the hard drive. You simply demagnetize the whole thing. So then you also need to think that the plate is spinning with a constant angular velocity. However, at the center, the linear speed will be much smaller than at the periphery, right? So data will slide under the head here slower and faster here. You also need to take this into consideration. So then one thing that I just want to give to you is if I write a file on disk, how should I put its clusters on the track? One, let's say, intuitive thing would be to simply put its clusters next to each other, right? So then you read 0, and then 1, and then 2, and so on. However, after you read the cluster, you'd have to transmit it, and there will be a little lag. And while that lag is happening, the next cluster will pass under the head. So you're not going to be able to read cluster 1 after you finish reading 0. You'll have to wait for the disk to spin again, which would suggest that if you put your clusters on the track, skipping every other position, while you transmit the data, you can transmit the data while this cluster, which is not the next that you want, slides under the head. And when you're done, 1 is right under the head. If the lag is larger, then you can do this kind of placement with 2 spaces in between every consecutive cluster. So these are things that the file systems and hard drive makers are taking into considerations and are optimizing. There are more things to see here. You can check them in these files if you're interested. You have them on Piazza. But this is where I will stop. So the things that I'm asking for exams are everything I've said just before this piece. I will leave this out. So now let's talk about the Mars Pathfinder. I asked you to read the story. I'm not sure you did. So I'm going to try to retell it in a way that might be a little more accessible to you. So it goes like this. NASA sends a robot to Mars. The whole thing is a success. The disk defragger, yeah, the disk defragger is not really responsible for where the clusters are on the disk. It's more like where the clusters are in the FAT, but also on the disk probably. So yeah, the defragger might hit this as well. So let's talk about Pathfinder. So this robot reaches Mars, lands, all a success. It lands, I believe, with some inflated balloons around it. So I visualize as it bounces off the surface of Mars till it stops. Then it turns and it opens up and it starts doing things. However, every once in a while, it reboots. It just resets. And in the process loses some data, which, given the amount of effort and cost involved in this, is not really something you want. However, NASA was able to fix the problem and everything went on just fine. Now, what was happening? What was the problem? So the first thing to know is that a robot such as this is actually not one computer. It has many embedded things that can communicate between them. You can imagine every wheel having a little controller with its little processor. Every antenna, every sensor will have its little thing. And then you'd have a central processor which communicates between this, right? Sends messages from one to another. So in this robot, the operating system had a thread which was called bus, and it was responsible for just dispatching messages. This is the central activity. Without this, nothing happens. It's essential that messages are dispatched in a timely manner. Why? Because this is a mechanical thing. And messages control its actuators, its motors, its whatever it has. So if a message doesn't get there in time, a motor may overspin and maybe breaking something. Maybe a message doesn't get in time, the wheel spins a little more and the whole thing goes into a crevice, right? It just falls off the cliff. So timeliness is really important here. So this bus thread had a high priority, larger than any other thread, because it had to move things around, which was essential. Besides this thread, the bus, there was a weather thread. Now, the weather thread was something of a infrequent operation. It only popped up every now and then, every 5 minutes, checking to see if it rains, maybe. I'm not even sure it rains on Mars. But, you know, weather doesn't change from a millisecond to another. So it wasn't something very frequent, and it had a low priority. Low priority and kicking in every now and then. And then there was a middle priority thread, okay, which was doing other things. So let's keep in mind priorities, okay? You have the bus, which has high priority, and it does a lot of work. You have the weather, which has low priority, and it doesn't even do much. So when it does it with low priority. It's not very frequent. And even when it gets processed, it has a low priority. And then you have this middle priority thread, which does other things. Now, the last piece of the setup is that the bus and the weather use the same mutex. Both of them locked the same mutex. So the cause of the reset was the following. Every once in a while, the weather would catch the mutex. But then being low priority, it would be, let's say, pushed off the processor by the bus. So the bus gets the processor, and the bus also reaches the point where it needs to lock the mutex. Mutex, however, is taken by weather. So then bus has to wait. Then the processor is to be split between the weather and the middle priority thread. And because weather has low priority, the middle priority thread every now and in a while would kick it off the processor so that it would work. So the mid priority thread would keep the weather off processor with the mutex taken, which would make the bus wait. And if the bus was inactive for too long, the whole system decided, well, there is an error, there is nothing moving, so we will reset. So this was the problem. This goes to show you that working with threads makes things complicated in ways you wouldn't expect. If you have no synchronization, the data gets corrupted. If you add synchronization, then you risk deadlocks. If you add priorities to synchronization, then you may end up with this kind of situation where a thread is starving because although it has higher priority, it's waiting for a mutex held by a low priority thread. And that low priority thread is simply knocked off the processor because other threads have to do stuff which have a medium priority. The solution to this is in the attributes to the mutex. In the POSIX mutex, the second argument, when you initialize a mutex, would accept a number of attributes. We didn't cover those, but I'm going to tell you one of those attributes. So one of those attributes would tell the mutex something like this. Whenever a thread locks you, give that thread as priority the highest priority of all the threads waiting at the mutex. So, when the weather thread gets the mutex and the bus thread waits at the same mutex, the weather thread should not run at its low priority because it risks being put off the processor in favor of the medium thread. As long as the weather holds the same mutex with the bus, the weather should have the same priority as the bus. As soon as it drops the mutex, the weather goes again at its low priority. And this is configured with this attribute in the mutex. You just tell the mutex, thread holding you should get the maximum priority of all the threads waiting. So NASA was using this system called VxWorks, very, very nice real-time system. And they were inspired to leave this debug option on when they sent the robot to Mars. So they were able to actually write a patch for their code and upload it to Mars, which is pretty impressive. And the robot received it, patched itself thanks to a feature in this operating system, and then everything was fine. All it took was set this option to the mutex. So now if you reread the story, you might get more out of it because there are a few more details there. But this goes to show you the complexity of concurrency, and that you should always use your logic and pay attention to it. So with this, I'm done teaching for this semester. That's all, guys. We're done. We only have to talk about the exam. Before that, just a few quick words. The goal of this system, of this course, was to teach you to use the resources of the operating system and also learn how to work within the limits that those resources impose. So how do you use the cores, threads, processes? How do you how do you synchronize? How do you work with files? All this. How do you use commands that exist? So the shell part is supposed to make you more proficient. Maybe you've seen. I posted a link the other day. I really enjoyed it. Oh, don't get emotional. No. Don't worry about it. It's been only 14 weeks. So I posted this piece of news that they were using awk, grep, and sed for high performance massive data processing, which is really good. I'm using the tools of Bash on a daily basis, and I'm much more proficient than without them. Basically, well, thank you. Basically, knowing these tools will kind of transform you from a person who clicks on things to a person who treats its data and files with programs. And those programs are written really, really easily with very expressive commands. Although they're weird, but once you get through the weirdness, you'll be very efficient. So that's the shell part, that's the point of it. This other part of it is to learn what's in an operating system, how do you use it, and be exposed to the fact that your programs do not live alone on a computer. This morning, just to give you an example, this morning I had an exam with some of your colleagues, and for the first time in their life, they got malloc giving an error. Because I reduced the size of the exam server to fit in the budget, and we were too many on the system, and malloc would fail. Malloc doesn't really fail often, but it did now. So you are practically working within limits. You need to know that they exist. All right. So this was the whole goal. Understand concurrency, understand synchronization, understand resources, and know how to use the system in another way, not just with clicks and windows. Program your system with shells. You can do that in PowerShell in Windows. You can do it in Bash, in Mac and Linux. And then, let's be honest, what's the most popular, what's the dominant operating system in the clouds, including in Microsoft Cloud? It's Linux. So we're gonna have to deal with it. All right, that was it. Exam. Windows 7? Yeah. I've been using Windows 7 until this semester, I think. I just didn't want to upgrade, but not for servers. So, exam. I've posted the exam dates. You've seen there are lots of links. You'll have to do modulo your student ID to figure out which Jitsi meeting to join, because we cannot have everybody in the same meeting. We're too many. And the exam will go just like it did before. You log into the server. You'll have, I think there will be several files, each with the subject to answer with a problem. You'll answer it in a problem, in another file, and you're done. So you have to use a command line editor. You also have the command line resources available to you. You can have a legal cheat sheet, which should be A4, front and back, double-sided, written by hand, readable by the human eye. So no, microscopic handwriting. You'll scan it or photograph it, I don't know, and you can have it on the screen. You can have these two pictures on the screen in front of you when you do your exam, and we'll see them when you share the screen. You'll have to answer these questions. Now, these questions will not really be problems, although sometimes I might give something that asks how some code behaves. You'll have to understand the theory, you'll have to understand the concepts that we talked about, and answer those questions, understanding what's behind. The answers normally will be short. When I give this exam on paper, it's really no, sorry, Water Addict, don't write it in an a.txt, because you can do that with copy paste. I'm actually quite tricky here. The cheat sheet is not really meant for you as a reference in the exam. It's meant as a learning tool. As you write it by hand, you will learn. If you do it in a text file, that's just gonna be copy pasting and no learning. So I'm mostly manipulating you here, really. Also, we will see this cheat sheet. Please do not have the same cheat sheet as other colleagues, because we will see them, and then we will ask you to close them. Okay, so it's important. Yeah. All right. So the answers will be expected to be concise. No writing of everything you know. Just answer the question. So here is a question that actually I will ask. So it's like a bonus, but to my surprise, few people actually get it. Now that's recorded and online, maybe more people will get it. So one of the question is, how do you prevent a deadlock? And the answer is really short. Choose an order for your resources and always lock them in the same order. That's it. Okay, if your handwriting is not good enough, well, since you're stuck at home, yeah, you can ask somebody who has a nice handwriting, but they will hate you for it because there is a lot of stuff you can write on a piece of paper of that size. I've seen people really just giving up on this cheat sheet. It's your choice. Okay, so that's the written exam. Do you have questions about the written exam? 10 or 15. 10 or 15 questions, I think. I haven't really decided yet. You'll have 1 hour for the written exam. About the grades, they will come. You will get an email with a full email report and the details of what is what and what is not and what should be retaken and so on. All right. Other questions, or can we move to um, the re-examination? I want to have some details on that as well. Okay, thank you. Yeah, they will be updated post factum, but I have found a set of older teaching notes and I will upload those. They're not in the same spirit of the ones that you've been using, but you will find stuff about threads and the synchronization mechanisms. So I'll put those on the website. I'll put those on Piazza. You will have them today or tomorrow. All right, re-examination. Okay. Okay, so let's talk about a re-examination. Now, there are two kinds of re-examination, fast and normal. The fast one is meant to reduce the number of people that we have to process because it's 1 day and potentially you can have 400 people and we cannot do that. You're too many for us. So then people who have 8 or 9, depending on the situation, may opt to go for the fast re-examination. If there are many of you, I will actually enforce that you have to take the fast re-examination because I have no choice. Fast re-examination means 3 questions, each question half a point. You answer it, you get it. But when I say 8 or 9, I'm talking about the final grade. So if you have the final grade with everything combined, either 8 or 9, then if you have an 8 and you want 10, answer 3 questions, that's 9.5, and we round it to 10. If you only answer 1, that's 8.5, we round it to 9. Okay? So that's the fast re-examination. Do I recommend it? Obviously, yes, because I'm making it so that things are moving faster. But if you feel that you'd have better chances taking the other one, then take the other one. But you cannot have both because then it just defeats the purpose. The normal re-examination has at most 4 parts. Written exam, practical shell exam, practical processes and threads exam, and another one which replaces the lab average. Yes, the questions in the faster examination will be somewhat harder, but not crazy hard. They will be somewhat harder. It will require you to think a little more. Yeah, about, I would say, 75% of the students that came to the faster examination got a higher grade. I don't really have the numbers, but that's my impression. How much of this last theoretical part will be covered in the exam? All of it. So those questions will cover everything we've talked about. So we have 14 lectures. I will have questions covering everything that we talked about in those lectures. So the re-examination will happen all in 1 day. Okay, you come in, you log into the system, and then in that account you will have the 4 problems: written, practical shell, practical processes, threads, and lab replacement. You tell us which one you want to solve, which ones you want to solve, and then you'll have an hour for the written and 20 minutes for each of the other ones. When you're done, we grade them, and if the grades that you're getting are higher than the ones that you had already, We'll take them into account. If not, not. And that's about it. Okay, headshot spy. If you have a 9, it's enough to answer correct one question. One of 3. Because we round up. So you get 950, and that's a 10. That's it, guys. So let me know of any other questions. Yes, yes, Steph, you can have a cheat sheet for the fast written exam. What I cannot do is take your cheat sheets, because I used to do that. So after the exam, I would take the cheat sheets. So you'd have to write another one for the re-examination. But now, what am I going to do? I cannot do that. So you lose a chance of learning more. Anybody else with questions? Yeah, maybe. Maybe I'll ask you to give me control over your computer, whereas your cheat sheet is on your phone, right? What's the structure of the what do you mean, what's the structure? 10, 15 questions, and you write the answer to them in text files, concise answers, that's it. Oh, okay, so then just watch the recording. You'll have all the details there. The grades, well, I'm doing my best to send them to you this week. You will get them. They are in place. I just need to write the code that sends you the email, because this whole thing is being built as we use it. All right, anybody else? There is a centralized list. You just haven't. They should actually plug them into the system. It's all right. You'll get emails with all your grades. Okay. No more questions then? Are we fine? Can... Oh, but you will know. You will know. You'll know hopefully this week. You will know. It's not harsh. You probably passed. Or not? I don't know. I'm not gonna be mean. We'll see. It's 50-50 as of now, because we know nothing about your answer, but maybe it's more than 50-50 towards a good outcome. All right then, guys. That's it. 14 weeks, 3 normal, 11 crazy. We're done. Looking forward to vacation, but we still have to go through the exams. Schrodinger's pass. That's funny. All right, so I'm gonna stop here. I'll upload all this stuff to YouTube so you can use it as reference. Look for those. Wait a second. I can hear you laughing, but can you hear yourselves laughing? I mean, are you all in a conference? All right. So enjoy the rest of the day. Good luck with the exams this week. Oh, you can hear yourself. That's good. That's a plus. Enjoy the rest of the day. Good luck with the exams this week and in the upcoming 3 weeks, and then we relax a little bit. Take care, guys. I'm stopping here. Bye bye.